Have you ever tried to put together one of those massive jigsaw puzzles, only to slowly realize that the pieces belong to two entirely different pictures?
Oh, that is the worst feeling.
Right, like you have the edge pieces and they form this beautiful, perfectly crisp, predictable landscape.
Yeah.
But the center pieces, the ones you've been struggling with for hours, they seem to be cut from a completely chaotic, abstract painting.
Completely different art style.
Exactly. And no matter how you rotate them, no matter how hard you push or try to force the cardboard, they just refuse to lock together.
Which is incredibly frustrating.
It is. And that frustrating, seemingly impossible puzzle is actually a pretty accurate representation of the current state of modern physics.
I mean, that is spot on.
Because for roughly a century, we have had general relativity. This is the physics of the very big, right?
It's a cosmic scale, yeah.
It governs stars, galaxies, the bending of light, the immense pull of gravity. It is smooth, it's continuous, and highly predictable.
Beautifully predictable math.
But on the other hand, we have quantum mechanics, the physics of the very small.
Atoms, subatomic particles, quantum fields.
Yeah, and this world is jumpy, probabilistic, and entirely discrete.
It's a completely different rulebook.
And both of these frameworks are phenomenally accurate in their own respective realms. I mean, both have been proven time and time again by some of the most rigorous experiments in human history.
Down to absurd decimal points.
But for 100 years, they have absolutely refused to fit together into one unified, cohesive picture of reality.
It really is the ultimate scientific stalemate. And I think it's important to emphasize for you listening, this isn't just a minor academic disagreement happening in the halls of universities.
Right.
It is a fundamental, glaring incompatibility at the very core of how we understand the universe. Physics has essentially been stuck.
Stuck is a good word for it.
We're relying on two completely separate rulebooks to describe a single universe, and those rulebooks directly contradict each other the moment you try to read them at the same time.
Like when you try to look at something that is both incredibly massive and incredibly small.
Exactly, like the center of a black hole or the very beginning of the universe. The math just breaks.
Which brings us to our objective for today. Welcome to this deep dive. We have an incredibly unique stack of sources to go through today, and we are going to be spending some serious time really tearing it apart.
I am so ready for this one.
We are unpacking a draft paper and a fascinating collection of background notes titled Mode Identity Theory V7. It's a draft. And our mission today, to explore a radical new framework that attempts to take those two incompatible puzzle pieces and entirely redefine the shape of the puzzle itself.
Which is a bold claim.
Very bold. But here is the piece of context that makes this so fascinating. This theory is not being proposed by a tenured theoretical physicist at a massive research institution.
No, not at all.
It comes from an independent researcher, a civil and forensic engineer named Blake Shadow.
And that specific outsider perspective is exactly what makes this document so compelling to analyze. Because the core thesis of mode identity theory, or MIT for short, requires a massive philosophical paradigm shift.
Okay, lay it out for us.
So standard physics tells us that the universe is fundamentally made of tiny bits of matter, particles. And these particles sometimes exhibit wave-like behavior depending on how you measure them.
The classic wave-particle duality.
Right. MIT takes that entire premise and flips it on its head. It asks a really profound question. What if the universe isn't made of fundamental particles at all?
Wait, no particles?
None. What if, instead, the universe itself is a single fundamental resonating wave, and what we call particles are merely the universe taking a geometric reading of that wave?
Okay, let's unpack this.
Yeah.
Because reading through these notes, the author has a highly distinct, incredibly confident voice.
He really does.
He doesn't write like a cautious academic hedging his bets to survive peer review. He talks about treating complex Fourier transforms like fun little math puzzles.
Yeah, casual evening math puzzles.
He discusses his background, taking down buildings in his dad's demolition company. He literally drops lines in his margins like, haters eat your heart out.
It's amazing.
It's a very unconventional tone for a physics paper. Definitely more internet forum than academic journal.
It is definitely unconventional. There is a tangible swagger to the writing. But while we can acknowledge that tone, it's crucial to maintain an objective distance here and look at what he is actually presenting.
Right, look past the swagger.
Exactly. Because what elevates this draft beyond just a late-night internet thought experiment is that the author presents extremely rigorous math alongside the bravado. Mode identity theory locks in very specific, falsifiable mathematical predictions.
Yes, the predictions are key.
He is laying his cards on the table ahead of a massive influx of new, highly anticipated telescope data. This is data arriving from the Euclid Space Telescope in October 2026.
He's putting a timer on his own theory.
He really is. He isn't asking the scientific community to just trust his philosophy. He is essentially saying, here's the math, here's exactly what the telescope will see in a few years, and if the data contradicts me, the theory is wrong.
That is bold.
That level of falsifiability forces you to take the actual claim seriously, regardless of the tone.
And that is exactly why I wanted to go so deep on this today. Let's start with the author's background. Because as I was reading, I realized his background as an engineer heavily informs the entire foundation of the theory.
Oh, absolutely. It's the core of it.
He's a civil engineer. He grew up working in demolition, literally analyzing how structures fail and tearing them apart. And then he went to school to learn how to build them back up.
Which is a very specific way to look at the world.
Yeah, he works in construction management and forensic engineering, which essentially means he is the guy they call when a building collapses or a bridge fails, and he has to reverse engineer the disaster.
A literal deconstructionist.
Exactly. Yeah. And he minored in math and physics at Florida State University. He even casually mentions deriving the age of the universe using energy density for extra credit on a final exam.
Just for extra credit.
Right. While studying in Paul Dirac's old library. So let me see if I'm tracking the broader implication here. How does an engineer's mindset actually change the approach to a problem that theoretical physicists have been stuck on for a century?
It changes the approach at a purely foundational level. To understand why, we have to look at how physics is traditionally done. Modern physics is incredibly obsessed with measurement.
We love measuring things.
We build colliders that cost billions of dollars to measure the spin, mass, and charge of particles to mind-boggling degrees of precision. And then we build highly complex mathematical models to fit those specific measurements.
Okay.
But standard physics famously struggles to give the underlying constants of those models any actual meaning.
What do you mean by meaning? Like why the numbers are what they are?
Exactly that. For example, the standard model of particle physics has roughly 26 free parameters. These are numbers like the mass of an electron or the strength of electromagnetism that we just have to plug into the equations by hand.
Because that is what our instruments measured.
Yes. If you ask a physicist why the gravitational constant is that exact specific number, the honest answer is, we don't know, but that's what we measured.
Yeah, truth is what it is.
Exactly. Mode identity theory, driven by an engineer's mindset, treats the universe as a structural engineering problem instead of a measurement problem.
So treating it like a building.
Yes. In engineering, the topology, the foundational shape and geometry of the structure always comes first.
Makes sense.
If you build a suspension bridge, the load-bearing limits, the tension on the cables, the resonant frequencies, those aren't random numbers you just measure later and shrug at.
You hope not.
Right. They are a strict, mathematically unavoidable consequence of the bridge's initial shape. MIT applies this philosophy of derivation to the cosmos.
Okay, so the shape comes first.
The shape of the universe determines how the structure behaves. Observation simply supplies the scale of what you are looking at. And in this framework, every single universal constant is just a necessary, derived consequence of that initial geometry.
That is a massive leap from how we usually talk about cosmology. But I mean, it feels incredibly intuitive when you frame it that way.
It really does.
So in the draft, the author lays out 5 foundations to effectively invert standard physics. The first one is what he calls wave-matter identity. He brings up Louis de Broglie, a French physicist who won the Nobel Prize for his work in the 1920s.
A giant in the field.
Huge. De Broglie gave us a famous equation, lambda equals h over p. Now, the way I learned this in basic physics and the way standard quantum mechanics teaches it is that this equation proves matter behaves like a wave.
Yes, it's the classic wave-particle duality.
Right. Sometimes light acts like a particle, sometimes it acts like a wave.
That duality is a cornerstone of standard quantum mechanics. The idea that a particle, like an electron, propagates through space as a wave of probabilities.
Probabilities, right.
But when you actually measure it, that wave collapses into a single definitive particle point.
But MIT argues that interpretation is entirely backward. MIT says matter doesn't behave like a wave. Matter is a wave.
A phase wave.
Specifically a phase wave, yeah. And what we interact with and perceive as solid matter is just a localized sample of that continuous wave.
This is a vital distinction. And the author notes that de Broglie himself actually insisted this phase-wave interpretation was the fundamental reality.
De Broglie actually believed that.
He did. De Broglie didn't like the prevailing idea that particles were bouncing around on waves of pure probability. He believed the wave was a real, physical entity.
So what happened?
He faced massive pushback from heavyweights like Niels Bohr and Werner Heisenberg, and ultimately, de Broglie's physical wave interpretation was pushed aside in favor of the probabilistic model we use today. De Broglie essentially abandoned that line of thought before his death.
Wow. And the author leaves a rather cheeky tribute to de Broglie in the notes, writing, "I got you, big dog. R.I.P. goat."
Which is just classic internet-era tone.
Totally. Acknowledging that absolute internet-era tone there.
Mm.
But practically speaking, if we accept this premise that everything is just a fundamental wave and particles are just samples, what does that actually change for a physicist working today?
What's fascinating here is the WHY behind this inversion, because it entirely changes which questions are allowed to be asked.
How so?
Well, in standard physics, because we believe fundamental particles exist, we spend astronomical amounts of money looking for them.
Like the Large Hadron Collider.
Exactly. When we see extra gravity in a galaxy holding the stars together, we assume there must be invisible particles causing it. So we spend decades looking for dark matter particles.
Right.
In the MIT framework, because everything is structurally a wave, you completely stop looking for invisible particles to explain anomalies.
Because they don't exist.
Exactly. Instead, you ask, how does the geometry of the universe behave to produce this effect? The anomalies stop being missing pieces of physical matter and start being recognized as structural features of the shape itself.
That is an excellent transition point. Because if everything is a wave, that begs an immediate, obvious question. A wave has to travel on something or through something.
It needs a medium.
Exactly. An ocean wave travels through water. A sound wave travels through air. So if the universe is a wave, what is the actual shape of the pool this wave is rippling through? What is the shape of the universe?
That's the big question.
Let's contrast MIT's answer with what standard cosmology says. Standard cosmology says the universe started with a singularity, the Big Bang.
Right. A singularity is a concept where all matter, all energy, and all of space-time itself is compressed into an infinitely small, zero-dimensional point of infinite density.
A point.
And then it exploded outward.
But MIT completely throws out the singularity. It says you don't start with a point, you start with a surface.
Exactly. And this is where we have to wade into some topology.
The mathematical study of shapes and spaces.
Right. To understand the universe's surface in MIT, we have to visualize what the author calls a nested topology.
Nested, like Russian dolls.
Kind of. He outlines 3 distinct nested layers. First, imagine a one-dimensional temporal edge. Think of it simply as a closed loop. In mathematics, this is called an S1 manifold.
Okay, a 1D closed loop, like drawing a simple circle on a piece of paper.
Perfect. Now, that 1D edge forms the boundary of a 2-dimensional surface, but it is not a flat surface like a sheet of paper. It is a Möbius surface.
Möbius surface.
And finally, that 2D Möbius surface is embedded within a highly specific 3-dimensional space known as a hypersphere or an S3 space.
Hold on, let me just wrap my head around this because those are some heavy geometric concepts. Let's break down the Möbius surface first.
Let's do it.
If I take a regular leather belt, give it 1/2 twist, and then buckle it together, I've made a Möbius strip, right?
Yes, that is the perfect physical analogy. And the defining most important feature of a Möbius strip is that it is non-orientable.
What does non-orientable actually mean in this context?
It means it only has one side and one edge. If you take your finger and trace along the center of that twisted belt, you will eventually return to your exact starting point. But you will find yourself on the flip side of the belt.
Because of the twist.
Yes. You are upside down relative to where you started. You physically have to go around the entire loop a second time to get back to your true original starting orientation.
Okay, I can picture that.
In physics and mathematics, this creates what is called an anti-periodic boundary condition.
So if a wave is traveling around this twisted track, what happens to it?
Because of that half twist, when a wave completes one circuit, it flips its mathematical sign. The positive crest of the wave becomes a negative trough. It has inverted.
Okay, I have the twisted belt in my head. Now, you mentioned this belt is embedded inside an S3 hypersphere. That sounds like a sci-fi term. How do I visualize a hypersphere?
It's notoriously difficult to visualize because our brains evolved to see in 3 dimensions.
Fair enough.
Think about a normal sphere, like a basketball. The surface of a basketball is a 2D surface wrapped around a 3D volume of air. An S3 hypersphere steps that up one dimension. It is a 3D surface wrapped around a 4D volume.
Which hurts my brain to even try to picture.
Right, we can't easily picture the 4D part,
Yeah.
but mathematically we understand the 3D surface perfectly. It is a finite closed space with positive curvature.
Like Pac-Man going off one side of the screen and coming back on the other.
Kinda. If you traveled in a straight line in a hypersphere for long enough, you would eventually end up right back where you started, just like walking around the Earth. MIT states that the 2D Möbius twist is fundamentally embedded inside this closed 3D hypersphere space.
And the author explicitly states in the draft that he chose this incredibly specific nested shape purely on philosophical grounds before he ran any of the math.
That's the craziest part.
He basically says, Möbius bands are mathematically elegant, so let's embed one in a 3-sphere and see what happens. It almost sounds too simple.
It sounds simple, but the result is staggering. He embedded this twisted 2D surface into the 3D hypersphere mathematically, and suddenly, the fundamental constants of the universe just started falling out of the equations.
Just falling out.
What's fascinating here is that this specific topology wasn't retroactively chosen or manipulated to fit pre-existing data. It was chosen as a pure geometric exercise.
An exercise in elegance.
Exactly. And it turns out that this exact specific shape inherently possesses the exact mathematical ratios, limits, and values we observe in the physical cosmos.
That is wild. So if this nested, twisted geometry is the literal shape of the universe, the obvious question for anyone listening right now is, where are you and I in it?
We have to be somewhere.
Right. Standard physics often treats the observer, the scientist looking through the telescope, like someone sitting in the audience watching a play on a stage. We are treated as external to the system we are measuring.
Like an objective third party.
But MIT says no, you are standing on the stage. You are constitutively inside the system.
This is a vital concept in the draft called bounded evaluation. It means the universe is a bounded, finite domain. It has an absolute floor and an absolute ceiling. It spans from the absolute smallest possible limit of physical reality, which is the Planck scale. Below the Planck scale, the concepts of space and time essentially lose their physical meaning.
That's the floor.
That's the floor. We can assign the Planck scale a value of roughly 10 to the power of 0 degrees of freedom.
Let's define degrees of freedom for the listener so we don't lose anyone.
Simply put, degrees of freedom refer to the number of independent ways a system can change or hold information. Think of it as the total number of distinct slots or pixels available in the universe to hold data.
Pixels is a great way to think of it.
So the absolute microscopic floor is 10 to the power of 0. On the other extreme, you have the massive cosmic horizon, the absolute edge of the observable universe.
The ceiling.
Yes. This represents roughly 10 to the power of 122 degrees of freedom.
Okay, let me try a visual analogy to ground this.
Okay.
Imagine you are standing in a bizarre, theoretically impossible room. The ceiling of this room stretches up to an almost infinite height, 10 to the power of 122. But the floor is at absolute 0. It is the absolute smallest possible limit. Where do you, a human observer made of atoms and cells, naturally stabilize in this room?
You don't float to the top.
Right, you don't float to the infinite top, and you don't get crushed down into the microscopic floor. You stabilize at the structural midpoint of the room.
Precisely. And in a geometric exponential domain like this, the midpoint isn't calculated by just cutting 10 to the 122.5. You have to find the geometric mean.
Okay, the geometric mean.
The geometric mean is the square root of the total cosmic scale. So what is the square root of 10 to the 122? It is 10 to the 61.
10 to the 61.
Therefore, MIT positions the observer, which encompasses humanity, our physical bodies, our telescopes, our entire sensory perception, at the structural geometric midpoint of the universe, 10 to the 61 degrees of freedom.
Wow.
We don't just happen to be the size we are. We are structurally locked into the exact middle of the cosmic scale by the geometry itself.
That is a staggering implication. We aren't just randomly sized flesh bags wandering around. Our exact physical scale is a strictly mandated mathematical consequence of the bounded universe.
It's all structural.
Let's trace that logic further. If we are sitting at this geometric midpoint, how do we experience time? Because standard physics tells a very specific story about time. It says time began 13.8 billion years ago at the Big Bang, and it had been ticking forward like a clock ever since.
Tick-tock.
But MIT argues that time didn't begin at all.
This is where that 1D temporal edge, the S1 closed loop we discussed earlier, comes into play.
The loop.
In the MIT framework, time is not a flowing river that started from a single energetic source and travels infinitely outward. Time is literally just the phase location on that cosmic standing wave.
Location.
Yes, the author denotes this wave in the math with the Greek letter psi.
Wait, let's make sure we clearly define a standing wave versus a traveling wave.
Right.
If I throw a rock in a pond, the ripples move outward away from the splash. That's a traveling wave.
Right. But imagine you pluck a guitar string. The wave travels to the end of the string, bounces back, and interferes with itself. It creates a pattern that vibrates up and down, but the wave itself doesn't appear to travel left or right along the string.
It just hums in place.
Exactly. It is bound by the two ends of the guitar. That is a standing wave. The universe, because it is a bounded topological cavity, acts like that guitar string. It generates a standing wave.
So when astrophysicists say the universe is 13.8 billion years old, they aren't talking about how long a clock has been ticking. They're just stating our exact coordinate location on the guitar string.
Exactly. We are just at a point on the wave. The math in the draft calculates our current position on this standing wave. In wave mechanics, a full cycle of a wave is measured in radians, specifically up to 4 pi radians.
Okay.
MIT calculates that our current historical epoch is situated at a phase of approximately 5.22 radians.
5.22.
This means we're actually approaching what the author terms the turnaround at 2 pi, which is the amplitude minimum of the standing wave. Time is not a duration. Time is a spatial phase coordinate.
Okay, so if time is just a phase on a wave, it makes me wonder about the texture of this universe. How smooth is it? Does space and time flow perfectly, continuously, like a smooth sheet of glass?
Not according to this.
The draft introduces a concept called the 120 domain, which implies the universe is decidedly not smooth.
It implies a maximum resolution. To use a modern analogy, the universe is fundamentally pixelated.
Pixelated space.
Because this Möbius surface is embedded in a highly specific, positively curved 3D space, it cannot support infinite smoothness. It has a maximum sampling resolution.
Like a video game engine having a limit.
Precisely. And this resolution isn't arbitrary. It is derived mathematically from the innate symmetry of that 3D hypersphere. Specifically, it stems from something called the binary icosahedral group.
The binary icosahedral group. Let's translate that for the smart but uninformed listener, because that sounds really intimidating. I know an icosahedron is a 20-sided shape, like the dice you use in Dungeons and Dragons.
That's the perfect starting point. Imagine that 20-sided die. Now imagine rotating it. There are only so many ways you can rotate it where it looks exactly the same as when you started.
Right.
Those are its symmetries. Now, take that concept of a 20-sided die symmetries and apply it to the complex, curved, four-dimensional mathematics of the hypersphere.
Okay.
When you map those symmetries out, the math strictly dictates that this spatial geometry can only resolve a maximum of 120 discrete positions or states. That is the 120 domain. Space cannot be divided any finer than those 120 steps.
That is wild. But what I loved in the notes is that the author takes this dense mathematical concept and connects it to something deeply human. He connects this 120 position limit to music.
If we connect this to the bigger picture, it is incredibly poetic. The draft notes that musical consonance ratios, the specific harmony that makes chords sound pleasing to the human ear rather than discordant noise, universally converge around the number 120.
Universally.
Across almost all global musical traditions, totally independent human cultures have settled on these exact same harmonic ratios.
Wow.
The author is suggesting that the human ear is literally a physical phase detector. We perceive harmony and beauty when physical sound waves align cleanly with the fundamental 120 resolution of the universe itself.
We literally hear the geometry of the universe. That is beautiful. But here is where the physics gets a bit more complex. The draft introduces a mechanism called the bosonic filter.
This is crucial.
So we have this 120-step maximum resolution. The building blocks of matter fermions, like quarks and electrons, can mathematically see all 120 steps. They experience the universe in its full resolution.
Right.
But when an observation actually happens, everything changes.
Right. In quantum mechanics, an observation occurs when a boson-like a photon of light interacts with a fermion. To calculate the probability of where a particle is during that interaction, the mathematics require the wave function to be squared.
Let me make sure I'm following the logic cascade here.
Yeah.
We talked earlier about the Möbius strip having an anti-periodic boundary.
Yes.
It flips the wave from positive to negative.
Right.
Fermions experience that entire wave, both the positive crest and the negative trough.
They see the whole thing.
But when observation happens, when light hits it, the math squares the wave. And what happens when you square a number? The negative signs disappear.
Exactly. The square a negative number is a positive. The act of observation erases the distinction between the positive half of the wave and the negative half of the wave.
Because they both become positive.
Yes. You lose the mathematical ability to tell them apart. Because you've collapsed those two halves into one, you mathematically have the resolution of the universe. The 120 position domain is immediately filtered down to a 60 position observable grid.
So the very physical act of light interacting with matter, the act of observing the universe, it literally cuts its geometric resolution in half. You are locked onto a 60-step grid.
You're stuck in the 60 steps.
And all of this geometric scaffolding, the 60-position grid, the 10 to the 61 scale, all of it leads to the absolute centerpiece of the draft paper, the scaling law equation. The author claims he can derive virtually any physical constant of the universe from one single equation.
It is the master equation of the draft. It is written as A over A sub p is approximately equal to C of theta times the square root of omega to the negative n.
Okay, reading equations aloud on a podcast is notoriously difficult to follow. Let's throw out the letters and translate this conceptually. Imagine you have a master recipe for reality.
I like that. Let's break down the recipe. A is the value of whatever physical constant you are trying to find. Maybe you want to know the mass of an electron or the speed of light.
Whatever you're cooking.
Exactly. A sub p is its Planck's scale reference, the absolute smallest possible baseline ingredient. C of theta represents the physical position of that constant on the cosmic wave. Essentially, which specific slot is it sitting in on that 60-position grid?
So you take its position on the grid, and then you apply the last part of the equation, the dilution.
Yes. That grid position is multiplied by the inverse of the observer's scale. We established earlier that the observer's scale is the square root of omega, which is roughly 10 to the 61.
The midpoint of the room.
Right. So you are taking the constant position on the wave, and you are diluting it or shrinking it down by the immense 10 to the 61 size of the room you are standing in.
Got it.
And the final piece, the negative n, is simply the geometric dimension you are measuring in.
Right. If you are measuring something that lives on the 1D temporal edge, n is 1. If you are measuring something on the 2D Möbius surface, n is 2. If you are measuring something in the 3D space, n is 3.
So conceptually, the equation says the true value of any physical constant in the universe is equal to its geometric position on the cosmic wave, structurally diluted by the dimension it occupies and the scale of the observer looking at it.
Position diluted by scale. It's incredibly elegant compared to standard physics, where we just throw our hands up and say, well, the machine said the electron weighs this much.
We just accept the number.
But this equation says the electron weighs that much because it sits in this specific grid slot, in this specific dimension, viewed from this specific scale.
It gives it a reason to be.
So what does this all mean for the big mysteries in physics? The author claims that the biggest anomalies in modern cosmology, the massive gaps in our knowledge that keep astrophysicists awake at night, they aren't actually anomalies at all.
They are expected.
They're just natural, expected geometric features if you use MIT. Let's walk through what he calls the 5 anomalies. Let's start with anomaly 1, the Hubble tension. Explain why cosmologists are currently in a state of mild panic over this.
The Hubble tension is arguably the biggest crisis in astrophysics today. Simply put, the universe is expanding. We know this. But when we try to measure exactly how fast it is expanding, we get 2 completely different, conflicting answers depending on how we look at it.
2 different speeds.
The first method uses what we call the distance ladder. We look at objects relatively close to us, specifically Cepheid variable stars in nearby galaxies.
Oh, yeah?
These stars pulse at highly regular intervals tied to their true brightness. They act like cosmic lighthouses. By comparing their true brightness to how dim they appear to our telescopes, we can calculate exactly how far away they are and how fast they are moving away from us.
So that gives us a localized speed limit for the nearby universe.
Yes, and that local measurement consistently comes out to an expansion rate of around 73 kilometers per second per megaparsec.
73.
But there is a second way we measure expansion. We look at the absolute furthest edge of the observable universe. The cosmic microwave background, or CMB.
The oldest light.
Exactly. This is the fossil radiation left over from the very early universe. We look at the tiny temperature ripples in this radiation, run it through our standard cosmological models, and predict what the expansion rate should be today based on the early universe.
And that number strongly disagrees with the local stars.
Vastly disagrees. The CMB method gives an expansion rate of roughly 67.4.
67.4 versus 73. That's a big gap.
For a long time, the scientific community just assumed our telescopes were slightly off or there was some dust in the way messing up the local measurements. But recently, with incredibly precise instruments like the James Webb Space Telescope confirming the Cepheid measurements, the error bars have shrunk to almost zero.
It's not a mistake.
It is not a measurement error. The early universe and the local universe are fundamentally disagreeing, and standard physics has no mechanism to explain why.
But MIT offers a purely geometric fix based on what we just learned about the grid. The theory introduces a concept called the phase field.
Right. Remember the master equation. Everything is about taking a reading from a specific position on the 60-position grid. But we don't live in empty space. We live inside a massive galaxy, the Milky Way.
Which is heavy.
Very heavy. And a galaxy has an immense, dense, localized gravitational field. MIT calculates that this extreme local gravitational environment acts as a phase field. This local gravity physically shifts our observational anchor point on that cosmic standing wave.
It nudges us.
Specifically, the math dictates it shifts our local observation point by exactly one minimum step on the bosonic grid.
One step out of 60. And the math in the draft shows that shifting our observational anchor by that single step results in an exactly 8.4% difference in the amplitude of the wave we're reading.
Which perfectly bridges the gap of the Hubble tension.
Oh, wow.
The local Cepheid measurements calibrate to a gravitationally shifted anchor point, yielding the higher value of 73. The CMB measurements, which look across vast, empty gigaparsecs of deep space, are unaffected by our local galactic well.
So they give the unphased reading.
Right. They give us the true unphased baseline value of 67.4. The brilliance of MIT here is that it says both measurements are completely 100% correct.
Nobody's wrong.
We don't need to invent new physics. We are just sampling the exact same universal wave from two slightly different geometric positions.
It's like measuring the temperature of a massive room while standing right next to a blazing radiator versus standing in the dead center of the room. Both thermometers are working flawlessly, but the local environment fundamentally shifted the reading of one of them.
That is a perfect analogy.
That is brilliant. Let's move to anomaly 2. The cosmological constant, often denoted by the Greek letter lambda, and tied to that, this concept of 3/2 gravity.
Lambda, often referred to as Einstein's famous biggest blunder.
His biggest mistake.
Back in 1917, Einstein added the constant lambda to his equations of general relativity. At the time, everyone believed the universe was static, but his equations suggested it should be collapsing under its own gravity. So he added lambda as a repulsive force to keep the universe static.
Like a structural prop.
Yes. When Edwin Hubble discovered the universe was actually expanding, Einstein threw lambda out in embarrassment. But in the late 1990s, astronomers discovered that the expansion of the universe wasn't just happening, it was accelerating.
Speeding up.
So standard cosmology panicked, revived Einstein's lambda, renamed it dark energy, and decided it must be some mysterious invisible fluid pushing the universe apart.
A dark fluid that makes up 68% of the universe, yet we have no idea what it is.
None.
But MIT says it isn't a dark fluid at all.
Not even slightly. In MIT, lambda is entirely structural. It is simply the ground mode hum of the cosmic boundary. It is the baseline vibrational frequency of that 2D Möbius surface.
The hum of the surface.
And because it is structural, the math produces a highly specific ratio. Think about how observation works in MIT. The universe's boundary has an intrinsic 2D property, an eigenvalue, but we, the observers, perceive it through the lens of 3D spatial dynamics. We are looking at a 2D surface through a 3D space.
And mathematical translation between different dimensions is notoriously tricky.
It is. The mathematical interface connecting a 2D surface to a 3D space is governed by something called the Gauss-Codazzi equation.
The Gauss-Codazzi equations.
Think of them as the definitive mathematical translation manual between a flat 2D map and a curved 3D globe. They tell you exactly how much stretching or cost is involved in translating from one geometry to the other.
Okay, the translation cost.
When the author runs the MIT topology through those translation equations, the math yields a strict, unavoidable ratio, 3/2.
3 for the 3D space we observe through, and 2 for the 2D surface that holds the wave.
Precisely. And that 3/2 mathematical conversion factor is literally what we experience as gravity.
Wait, gravity is just the conversion ratio?
Yes. Gravity isn't some separate mystical force mediated by undiscovered graviton particles. It is the structural conversion cost required to translate the continuous 3D space into the discrete 2D surface observation.
That's incredible.
When you plug that 3/2 ratio into the scaling equation, The numbers match the observed cosmological constant, lambda, to within 2%. Einstein's constant wasn't a blunder. It is literally the geometric ground tone of a resonant universe.
That sets up anomaly 3 perfectly, because we just handled dark energy. Let's tackle the other massive missing piece, dark matter. Standard physics teaches that roughly 95% of our universe is made of stuff we simply cannot see, which is why we slap the word dark in front of it.
Right.
About 27% of the total universe is classified as dark matter. We see its massive gravitational pull holding spinning galaxies together, preventing them from flying apart, but we cannot find the physical particles causing that gravity anywhere.
And standard physics has tried very, very hard to find them. This leads into what MIT calls the null dark detection principle. For decades, scientists have built incredibly sensitive, multi-billion-dollar particle detectors deep underground like the xenon experiments, hoping to catch a WIMP, a weakly interacting massive particle.
They're literally waiting for a blip in a tank of liquid.
But they have found absolute silence. Nothing. MIT argues that we can't find the particles because there are no particles to find. The experimental silence is structural.
Structural silence.
Remember the master scaling equation we discussed? The n value dictates the geometric dilution.
Right. N equals 1 for the 1D edge, n equals 2 for the 2D surface, and n equals 3 for the 3D space.
Exactly. And pure 3D space has an n of 3. When you run n equals 3 through that scaling equation, the observable intensity of that domain drops exponentially by a factor of 10 to the negative 183.
That's a dilution so massive it basically zeroes out.
Furthermore, pure 3D space has no gauge fields.
Let's define gauge fields really quick.
A gauge field is essentially the mechanism required for a fundamental force to interact with matter. Electromagnetism has a gauge field, which is why magnets stick to your fridge and light hits your eye. The strong and weak nuclear forces have gauge fields.
But 3D space doesn't.
Pure 3D space, however, lacks these fields. So the 3D geometry of space exerts a gravitational pull because, as we just established, gravity is just geometry, but it is observationally null to any detector looking for a physical, electromagnetic, or nuclear interaction. It is mathematically invisible.
That completely recontextualizes one of the most famous astrophysical observations in history. The author brings up the bullet cluster to prove this point.
Ah, the bullet cluster.
For you listening, the bullet cluster is a famous image taken by telescopes showing the aftermath of two massive galaxy clusters colliding at millions of miles per hour. When astronomers analyzed the data, they saw two distinct things. The visible matter, the hot, glowing gas of the galaxies, collided and slowed down in the middle of the impact zone.
Like a car crash.
But the vast majority of the gravitational mass, the presumed dark matter, seemed to shoot right past the collision zone without slowing down or interacting at all.
Standard physics points to the bullet cluster and says, see? Invisible ghost particles shot right past each other while the normal matter crashed.
It is often touted as the ultimate proof of dark matter particles. But MIT offers a far more elegant geometric explanation that requires exactly 0 ghost particles.
Exactly 0. In the MIT framework, what you are seeing is a separation of topology. The pure 3D geometry of space, which carries the massive gravitational signature, simply passed through itself seamlessly.
Passed right through.
Why? Because pure geometry has no physical cross-section. It cannot physically collide with itself. Meanwhile, the baryonic matter, the hot gas, the stars, the physical stuff, lives on the 2D surface modes.
The surface.
And because it lives on the surface modes, it possesses gauge fields. So the surface modes electromagnetically collided, interacted, created friction, and slowed down in the center.
It's like two ripples on a pond passing perfectly through each other without stopping, while the physical leaves floating on the surface of the ripples violently crash together. You don't need a new invisible particle to explain the bullet cluster.
Yeah.
You just need to understand that the 3D space passes while the 2D surface collides.
It is so clean.
That is staggering. Let's hit anomaly 4. The CMB anomalies, or what the author poetically refers to as the axis of light.
We mentioned the cosmic microwave background earlier. It is our most detailed map of the early universe, essentially a snapshot of the oldest light we can see.
The baby picture of the universe.
But when cosmologists map it out, it has these persistent, bizarre flukes that standard cosmology simply cannot explain. For instance, there are missing large-scale waves, fluctuations that should be there but aren't.
Missing waves.
There is an odd parity preference, meaning the data is oddly asymmetrical. And most famously, there is an alignment of temperature fluctuations across the entire sky that physicists jokingly call the axis of evil because it defies the idea that the universe should look the same in all directions.
Standard cosmology writes these off as weird statistical anomalies, just bad luck with the data. But if the universe is bounded by that twisted Möbius topology we discussed in Part 1, none of these are flukes. They are exactly what you would expect to see.
Precisely. If you look at the geometry of a Möbius strip, it intrinsically possesses a twist axis.
Right, it's a twist in the belt.
So, of course, the CMB map has a preferred massive axis of alignment. We are quite literally seeing the foundational twist of the manifold itself imprinted on the oldest light.
It's a twist.
Furthermore, a Möbius strip naturally flips parity. That is the anti-periodic boundary condition we talked about, flipping positive to negative. So, of course, we observe an odd parity preference in the data.
It has to be there.
And lastly, because the universe is a bounded topological cavity and not an infinite expanse, there is a hard maximum size for a wave that can physically fit inside it.
It can't be infinitely large.
The massive large-scale waves aren't missing because of a statistical fluke. They are missing because they physically cannot fit inside the cavity of the universe. It is not an anomaly. It is the universe starkly revealing the geometry of its beginning.
Here's where it gets really interesting, because we've spent this entire time talking about the macro world, the cosmos, galaxies crashing, the massive expanse of the CMB, the scale of 10 to the 61.
Big stuff.
But MIT makes a bold claim. It claims that this exact same shape, this exact same nested topology, also strictly dictates the micro world, the quantum scale.
Yes. The underlying philosophy is that the same boundary conditions that govern the massive cosmic horizon also intrinsically confine and govern the microscopic quantum fields.
As above, so below.
The draft dives into an incredibly complex issue known as the Yang-Mills mass gap. To give some context, proving the Yang-Mills mass gap is one of the Clay Mathematics Institute's unsolved Millennium Prize problems.
A literal $1 million prize.
There is literally a $1 million prize for anyone who can solve it. In standard flat space, physicists struggle immensely to prove mathematically why quantum force fields have mass.
But MIT claims to solve it effortlessly, using geometry.
It does. It points out that the hypersphere space, S3, inherently has positive curvature.
The curve is the key.
Because the manifold is a finite, positively curved space rather than an infinite flat plane, the quantum fields are naturally geometrically confined. You don't need complex, unproven mathematical gymnastics to give the fields mass. The mass gap is an unavoidable, inherent consequence of living inside a curved geometry.
And it gets even more specific regarding the particles themselves. In the standard model of particle physics, we have exactly 3 generations of particles. For example, you have the electron, and then you have 2 heavier, unstable cousins called the muon and the tau particle.
Quarks also come in 3 generations.
Why 3? Why not 4? Why not 20? Standard physics has no explanation for the number 3.
But MIT does.
Of course it does.
If you take the specific topological space, modulo that binary icosahedral group we discussed earlier, the 120 symmetries, the resulting math dictates that there are exactly 3 and only 3 isolated flat connections or geometric vacua within the manifold.
3 slots.
Because the topology only possesses 3 distinct structural slots, there can only ever be 3 generations of particles. The number 3 isn't a random roll of the dice. It is a hard structural limit of the geometry.
And the author doesn't just stop at saying, hey, there are 3 generations. He actually builds a mass formula to mathematically predict the precise weights of these particles.
He predicts the masses.
The standard model has 12 fundamental fermions, and their masses seem completely chaotic and random. MIT assembles a formula using just 4 strictly topological inputs. No hidden variables, no tuned parameters acting as a thumb on the scale.
The results of this specific mass formula are truly striking. When you run the topological inputs, 10 out of the 12 standard model fermions fall strictly within a factor of 3 of their experimentally observed masses.
That's already incredibly close.
And 3 of them, the electron, the up quark, and the muon, hit within 2 to 6% of observed reality. Deriving highly specific particle masses from pure geometric topology to that level of accuracy without adjusting parameters to force a fit is practically unheard of in modern theoretical physics.
But there is a catch. Let me see if I'm tracking this correctly, because this seems like a massive risk for the author.
Yeah.
The formula produces a spreadsheet table of 24 possible entries. 12 of those slots perfectly match our known standard model particles.
Right.
But right in the middle of that table is a block of masses that do not align with anything we know.
Ah, yes, the dead zone.
The dead zone.
The MIT mass formula explicitly predicts 6 specific states that sit squarely at the electron volt to kilo electron volt mass scale. The catch, as you noted, is that there are absolutely no known standard model particles that match these masses.
Well, they're just empty slots on the table.
It's like having a periodic table with 6 blank squares right in the middle. We haven't found them yet, but the math insists they must be there.
So is that a failure of the theory? If it predicts things that don't exist?
It is quite the opposite. It is a highly testable prediction. It gives experimental physicists a massive, specific target to hunt for.
Go look here.
According to the topological, these states would be structurally confined to pure 3D space, which means they would have incredibly suppressed non-gravitational couplings. In plain English, they wouldn't interact with light or typical matter, making them agonizingly hard to detect.
Basically invisible.
But, crucially, they sit perfectly in the mass window where physicists are currently searching for hypothetical particles called sterile neutrinos or warm dark matter. If a particle collider or an underground detector eventually finds a state at these exact specific dead zone masses, it would be a monumental, undeniable validation of MIT's mass formula.
That is the beauty of theoretical physics when it's done right. You don't just explain what we already know. You point to a dark corner of the room and say, look there, you'll find exactly this.
You predict the future.
Okay, I have to completely geek out for a second about the next point in the draft. The fine structure constant, denoted by the Greek letter alpha. Richard Feynman, one of the greatest and most brilliant physicists of the 20th century, famously obsessed over alpha.
He called it a magic number.
He called it a magic number, which equals roughly 1 over 137. He famously said it comes to us with no understanding by man, like the hand of God wrote it.
It's the fundamental constant that governs the strength of electromagnetism, how light and matter interact.
Right. And the author of MIT openly admits he put the number 137 into his theory just to see what all the fuss was about.
And what he found when he applied the MIT framework to that magic number is remarkably elegant. Alpha is unique because it is a dimensionless coupling constant.
Meaning it doesn't have units?
It doesn't have units like meters or seconds. It is a pure ratio. Because it is dimensionless, it does not rely on massive cosmic scales like the Hubble radius. It resolves entirely at the fundamental grid level.
The 60-position bosonic grid we talked about earlier.
Okay.
The pixelated resolution of the universe.
Exactly. The grid has exactly 60 discrete positions, so the absolute minimum logical step you can take on that mathematical grid is 1 over 60.
To 1/60th.
By placing the observable in the 13th geometric well on that 60-position grid, which is mathematically the exact same geometric well that governs fundamental matter, the MIT scaling equation inherently outputs a value of 0.000733.
And the actual observed measured value of alpha in reality.
0.007297.
It nails it.
The geometric theory predicts Feynman's famous magic number to within 0.5% of accuracy, derived entirely from the basic step resolution of a 60-position grid. But it goes even further than that.
How so?
Quantum electrodynamics predicts that alpha isn't perfectly static. It runs or changes very slightly at extremely high energy levels. MIT naturally recovers this running effect.
It makes the change too.
As you mathematically move closer to the Planck scale, the absolute floor, the observer's domain tightens, the dilution factor of the room weakens, and the true value of alpha geometrically rises toward 1. The 1 over 137 value we observe in our daily lives is simply the universe's hierarchy expressing itself geometrically as you move away from the microscopic limit.
The author refers to it in the notes as the first step of realization. Man, that is incredibly satisfying to see a century-old mystery tied up neatly by a 60-slot geometric grid. But as we noted at the very beginning of this deep dive, a theory, no matter how elegant or mathematically beautiful, is only as good as its real-world tests.
It has to survive observation.
Which brings us to the ultimate crucible, falsifiability. The author isn't just dropping this on a message board to argue with people endlessly in the comments.
No, he is posting it, drawing a line in the sand, and waiting for reality to weigh in.
Yes, and the timeline for that reality check is imminent. There is a massive influx of pristine cosmological data arriving in October 2026 from the Euclid Space Telescope's Data Release 1. The author has locked in strict primary predictions that will unambiguously make or break mode identity theory.
He gave 3 primary predictions. First, the cosmic acceleration scale, denoted as a sub-zero, must mathematically evolve proportionally to the Hubble parameter over time.
Okay, that's one.
Second, the cosmological constant, lambda, must remain completely, perfectly constant. No evolving dark energy fluids or changing quintessence fields.
It has to be dead flat.
And third, the phantom crossing, which is the amplitude minimum of the cosmic standing wave we discussed, must sit exactly at a cosmological redshift of z, roughly equal to 0.66.
For you listening, redshift is how astronomers measure distance and time. As light travels across expanding space, its wavelength stretches out, shifting it toward the red end of the spectrum. The higher the redshift, or z number, the further back in time we are looking.
And a redshift of 0.66 corresponds to roughly 6 billion years ago.
The author is planting a flag exactly at that moment in cosmic history. He promises that if the Euclid telescope data contradicts these specific geometric numbers, he will personally slap a giant fail sticker on his own theory.
He accepts defeat if the math fails.
But if the data matches, if Euclid DR1 confirms these exact geometric signatures, standard cosmology is going to have a catastrophic amount of explaining to do.
It would undoubtedly be a seismic shift in the foundation of physics. It would represent a total, undeniable validation of geometrical topology over pure, disconnected measurement.
So let's bring this all together. What an elegant, mind-bending deep dive this has been. We started with a broken puzzle. A universe of disconnected, random constants, invisible ghost particles, mysterious dark fluids, and entirely incompatible rulebooks that physicists have been bashing together for a century.
A total mess.
And mode identity theory replaces it all with a single resonating shape. A twisted Möbius surface perfectly embedded in a curved hypersphere.
A cosmic standing wave.
Where everything we know, from the exact mass of an electron to the sprawling expansion of the cosmos, is just a geometric sample mapped onto a 60-position grid.
It replaces chaos and randomness with strict mathematical structure. It finally gives the fundamental constants of our reality meaning by rooting them in absolute geometry rather than mere chance.
As we wrap up, I want to leave you, the listener, with a final provocative thought to mull over. We spent the last hour talking about particles, gravity, and cosmic constants, all being nothing more than the universe taking a reading of a standing wave. And that specific reading is intrinsically based on the structural limits of our specific geometric scale, the 10 to the 61 degrees of freedom where we sit right in the middle of the room as observers.
The center point.
So, what does that imply for human perception? Is human consciousness, our very ability to perceive the universe, just another localized phase well on this grid? Think about the implications. If our physical and mental awareness is fundamentally bound by the rigid mathematical constraints of this 60-position bosonic grid, there might be entire layers of reality, entire frequencies of the cosmic standing wave vibrating right through the physical room you're sitting in right now.
Right through you.
But you structurally lack the geometric dimension to ever observe them. You aren't missing them because you aren't looking hard enough with your multi-billion-dollar telescopes. You are missing them because of the fundamental, inescapable shape of the space you occupy.
This raises an incredibly important question about the absolute limits of knowing. Science is built on observation, but MIT suggests we can only ever measure exactly what our specific geometry allows us to sample.
We are locked in.
The universe might be playing a symphony, but we are mathematically restricted to hearing only a single chord.
A perfectly orchestrated chord. Thank you so much for going on this dense, incredible conceptual journey with us today. The next time you step outside at night, I invite you to look up at the night sky. Don't look at it as a vast, terrifying void filled with random, disconnected, burning objects. Look at it as a precisely tuned instrument, a grand cosmic geometry that, through sheer mathematical elegance, simply allows us to hear the light.